In this video, I'm going to derive the oscillation period of a simple pendulum, how this oscillation period depends on the pendulum length and mass. Let's call m the mass of the pendulum, the mass of this small ball, which is hanging from a thread of length L. Okay, so we know that if we shift slightly by a small angle the pendulum rightwards and we release it, we release the mass m, then it will start swinging back and forth, and it will oscillate in this swinging by with a very well defined period. Now we wonder how this period depends on the length and the mass of the pendulum. Well, in order to analyze this situation and calculate the period, let's draw here a generic instant along the oscillation. Let's call theta the small angle that the thread forms with the vertical in this generic instant. And let's draw the forces that we have. We have the weight of the mass, which is m times g, where g is the gravity acceleration, and we also have the tension in the thread, which is pulling the mass upwards. Well, in this case, since the thread is not in the vertical direction, the tension T can be decomposed into a vertical component, which is T times the cosine of theta, and a horizontal component, which is T times the sine of theta. Now, if we assume that the oscillation takes place in a very narrow angle amplitude, so theta is never going to be a big angle, then we can focus on the movement in the horizontal direction, and we can neglect the slight shift that will take place in the vertical direction along the oscillation. So if we focus in the horizontal direction, let me first of all draw here an axis to keep track of the horizontal shift along the swinging of the pendulum. This axis x will be useful to locate the mass horizontally, right? Let's call 0, let's put the origin of this axis right in the vertical rest position of the pendulum, right? So in this case, in this generic instant I've drawn before, this will be the generic x coordinate, right? We wonder how this x coordinate relates with the theta angle. Well, if theta is very small, as we have said, we can write that x can be approximated by L times theta, which means that we can approximate the horizontal component of the shift by the length of the arc, right, from the rest position to the current position, right? So we have this shift here from here to here. We have a small arc here, and the length of this arc of circumference is L times theta, and this length is approximately equal to the horizontal shift, given that the theta angle is very small. So we want to focus on the horizontal movement, and we're going to neglect the little vertical shift that will take place along the oscillation. And we want to write Newton's second law. Newton's second law will take us to the movement equation of the pendulum, right? And from this movement equation, we will be in a position to derive the period. So let me first of all draw the horizontal force that we have here again, which is the horizontal component of the tension. And let's draw it in a green color here to highlight it more clearly, right? So we can write Newton's second law as follows. We have the force equals m times the acceleration. Acceleration, as you know, is the second derivative of the shift, right? The linear shift. In this case, we are focusing in the horizontal direction, so we want to write it just for the x component of the forces and of the accelerations. What is the horizontal component of the force here? Well, the only component that is horizontal here for the forces is actually the green one here, which is minus t sine of theta. I have written a minus sign here because this horizontal component of the tension is pointing leftwards, and we have defined as positive the right, the vectors that are pointing rightwards, right? So in this case, the tension, the horizontal component of the tension has a negative sign. And on the second member of the equation, we have m times the second derivative of the x. But the second derivative of the x can be approximated using this approximation by L times the second derivative of theta. So we write L times the second derivative of theta. Now, we can substitute more things here because, as I said, we can neglect the vertical movement and we can assume that the cosine of theta can be approximated by the unity. So, in this case, we can approximate T, the tension in the thread, by the value of the weight. Because vertically, if we neglect the vertical movement, then we can assume that there is an equality of forces vertically. So the vertical component of the tension is compensated by the weight. Both forces are cancelled, so we can write this approximation. Tension equals the weight. So we can substitute the T, the tension value in this equation, and we can also, I will write it down here, right? First. And we can also make an approximation for the sine of theta, because if theta is very small, we can approximate it, the sine of theta, we can approximate it by theta. So finally we can write minus m times g theta equals m times L theta second derivative. And we see that the mass cancels out, so the period is now, well, the equation of movement is not going to be dependent on the mass. And we can write this as the second derivative of theta equals minus g over L theta. Well, we have written the equation of movement. Right? With this equation, we know how the angle theta is going to evolve with time along the oscillation. This equation is the equation of a harmonic oscillator. We can identify that this is the equation of the harmonic oscillator. And from the theory of the harmonic oscillator, we know that the coefficient here gives us the frequency of the movement. So we can write that the square of the angular frequency of the harmonic oscillator equals G over L. So from here we get omega equals square root of G over L. And finally, from here we get that the period equals 2 pi the square root of L over G. This is then the expression that we were looking for, and this expression gives us the dependence of the oscillation period of the simple pendulum with the length of the pendulum. We see that it only depends on the length of the pendulum. It does not depend on the mass of the pendulum.